Hi, Professor.
Hello.
Uh, Professor, am I audible?
Good afternoon. Yes, you're audible. Can you hear me?
Yeah, you're audible. Clear. So, Professor, you will be sharing your slides, right? Uh,
Yes.
Let me make you co-host so that you can check. Yeah,
Sure. Please do. I'll quickly
yeah.
check.
Yes, I made you co-host.
Sure. Just give me a minute.
No, I don't think it's audible.
Please let me know when you can see the slides.
Yes, Professor, these are visible. Can you make it full screen? I think.
So, is this okay? You want me to?
Uh, can you press Control L or something?
So with that, I
Control Shift F or something.
can do that. Are you able to see the screen still?
Yes.
Okay, great. And it is changing, right?
No, here it's not changing, Professor.
Okay.
Now
That's
it's.
the reason I was not doing the.
Oh, okay.
Let me try again. Just a minute. Can you see the change slides now?
No.
Okay. Just give me a minute. Let me reshare them.
Huh.
Can you see this now?
Yes.
And is this okay? Or you want me to?
Yeah. This is fine, but can you? Yes. Now I'm seeing changes.
Okay, so this is better because this is not full screen at my end, but I think this is big enough for your
Okay.
eyes. Okay, great.
Mhm.
I think we started 5:30. We have sufficient time, right? So I'll go on mute maybe, and
Ah,
I'll come back in 5 minutes or so. Right?
sure, Professor. And
You're all
you are
set, right?
okay?
You need anything else from my side? The audio side is thing is clear, or you want me to use a headset?
No, it's really clear. And usually people will also unmute themselves and ask it.
Sure,
If there are some questions on chat box, I will relay it to you.
sure.
And you are okay with asking questions in between of the talk, right?
Yeah, in between is better
Okay, sure.
because
Thank you,
I'll also
Professor.
have the context. So, what is your good name again?
Srinivas, Professor.
Oh, you're the one connected on email.
Yes.
Okay, sure.
Yeah.
And you are a
I'm a PhD student here
okay. In whose
in
group?
IISc. Professor Parimal Parak,
Oh,
Network
Professor Parimal.
Distributed.
Very nice. Very nice.
Mhm.
Which stage of PhD are you in? Which year?
Fourth year, Professor.
Fourth year. Okay. Very good. Very good. Sure. Great. So thank you. Thank you for coordinating this. And let me quickly grab something to drink. And then I will unmute and I'll re-render the video. I am leaving the slide sharing as it is. I'm not changing that.
Okay, no issues,
Right?
Professor. That's fine.
Sure.
Yeah, thank you. Professor, shall we start?
Yeah, hi. Please go
Sorry,
ahead.
sir. Sir, Professor, let me introduce you and I will hand over the session to you.
Sure.
Thank you. Good evening, everyone. Welcome to the Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RBCCPS IASC. It's my pleasure to introduce today's speaker, Professor Abhinav Kumar, and he will be speaking on RIS-assisted NOMA communication under phase and SIC imperfections. Professor Abhinav received the dual degree in Electrical Engineering and Information and Communication Technology and the PhD degree in Electrical Engineering from the Indian Institute of Technology, Delhi, India in 2009 and 2013 respectively. From December 2013 to November 2014, he was a postdoctoral fellow at the University of Waterloo, Canada. Since 2014, he has been with IITH, where currently he is a professor. His research interests are in different aspects of wireless communications and networking, including 5G and beyond communications, Internet of Things, machine learning, security, and privacy. He is a senior member of IEEE and an editor of IEEE Transactions on Communications and a Young Faculty Research Fellowship awardee under Visvesvaraya PhD scheme of Ministry of Electronics and Information Technology, Government of India. He is currently the convener of the Faculty Section Committee for the Department of Electrical Engineering at IIT Hyderabad. We request the audience to keep your microphones on silent during the talk, except while asking questions. Questions can be asked at any time during the talk, either by unmuting and speaking directly or by typing them in the chat box. Over to you, Professor.
Sure. Thank you. Thank you, Srinivas, for the kind introduction. I hope I'm audible. And thank you for this opportunity to present this talk. So I'm going to talk about RIS-assisted NOMA communication under phase and SIC imperfections. And this is a broad outline of my talk. I'll start by introducing the problem and motivating why this is a relevant problem to work on, why NOMA with imperfect SIC is something that should be taken into consideration. And then I'll look at various other aspects beyond just the imperfect SIC's effect on NOMA. So we look at generalization beyond two users, what happens in presence of two users in terms of fairness, the scenario for uplink and downlink, and also for various use cases from a practical perspective. And then finally, towards the later part of my talk, I'll try to also touch upon the RIS-assisted NOMA with IPC or imperfection in phase compensation. And then I have a couple of slides toward the end just to highlight and motivate some of the things about my department and some of the conferences that I'm associated with. But maybe that toward the end. Without wasting any time, let me just try to introduce what the problem is all about. For those of you who are familiar with cellular network, there are two aspects that have been governing cellular networks since the very beginning or inception from the 1G time. Now we are already in 5G domain and people are already working on 6G aspects of the cellular network. But if you look back towards this whole journey from 1G, 2G, 3G to 4G and 5G and now 6G, two aspects have been very crucial in defining cellular networks. One has been reuse of the resources between users. So we want the network to utilize as much as possible or reuse as much as possible the resources. And primary resource in a cellular network is frequency, because spectrum is a costly component as far as the network goes. So frequency reuse is very important. But at the same time, if we can reuse as many of the other aspects of the network, nothing like it. So that's one part. And the second part is in terms of coverage. So we want mobility, we want as big coverage as possible within the association of one base station. So we would like to maximize coverage and we like to maximize reuse of the resources in the network. And that is how the network has also evolved. If you look at 1G, for example, it was frequency division multiple access. And then TDMA we had in 2G, where we moved to time division multiple access because it was relatively better. We only give resources to active users in some sense. And I'm going to skip CDMA in interest of time, but then we will chuck 3G out. But in 4G we had, and in 5G also we have OFDMA, where we are giving time frequency resources. You can also call them as the resource blocks. And we're trying to allocate them to a different user. So each color in this slide, for example, is a different user. Red, green, blue is a different user. And then we're giving them different components or resources in time frequency. And now, when we are moving beyond 5G, one of the potential multiplexes technique that has been championed across the globe is NOMA, which is non-orthogonal multiplexes. In this particular illustration, we are looking at power domain NOMA, where we are multiplexing users in the power domain. So green, blue, and red user, they get all the frequency and time resources at the same, but then we try to multiplex them in power. And I'll illustrate that in the next slide. How do we do that? This is one type of NOMA that is possible. You can also do it in code or other domains. But for our discussion today, we're going to focus only on power domain NOMA. So I'm going to just use NOMA and power domain NOMA interchangeably as far as today's session goes. So to elaborate more on power domain NOMA, effectively what we have is we have, let's say, 2 users, and we can generalize this to larger number of users also. We are going to designate them as a strong user, let's say US, and a weak user, UW, where this connotation of strong and weak comes from based on their channel gains. So we have a channel gain HS between the base station and the user US. We have a channel gain HW between the base station and the user UW. And again, for the first part of the talk or majority of the talk, I'm going to consider a downlink scenario where we are downloading data from the base station to the users, but an equivalent uplink scenario can also be considered with certain nuances in place. So if we have 2 such users, and under the assumption that the HS is significantly larger, or mod of HS square, I should be saying, is significantly larger than mod of SW square. So there is a gap in their channel gain. One is a strong or a good user, the other one is weak or a bad user. You can also view this from a distance perspective. If we are thinking from line of sight, that strong user is closer to the base station, weak user is farther away from the base station. Or equivalently, you can think of it as the weak user is behind a blockage and the strong user has a line of sight, right? So under this assumption that you have these 2 users, one strong and one weak, now in power domain NOMA, what we want to do is we want to multiplex them by giving small amount of power, a fraction of power to the strong user and a reasonably larger fraction of power to the weak user. And the motivation is as follows, that if the strong user's mod of HSW square is large, even if we give it small amount of power and we try to transmit both the strong and the weak user signal simultaneously, because the strong user is closer to the base station, it should be able to decode the weak user signal, right? Perform successive interference cancellation, remove that signal out of the received signal, and then try to next decode its own signal from the remaining component, right? Whereas for the weak user, because it is further away, even if we give more power to the transmission component of the weak user signal, because it is away from the base station or because the channel gain is poorer, it can only decode its own signal, which has been given. So as you see here, which has been given, more power. So here, as you see this UW, it has been given more power. So it should be able to treat the strong user signal as a noise and simply decode its signal UW. Because anyway, we are giving small amount of fraction to the strong user signal. The signal is almost like noise. US is almost like noise. A US signal of US is almost like a noise at UW, right? So that is what a 2-user NOMA system looks like. Traditionally, that is how people have been using NOMA. But then this whole system is based on an assumption that the strong user can successfully cancel out the interference from the weak user signal. Now, this assumption is a bit strong because this may not always be true. This is going to happen in hardware. So we are going to have hardware imperfections. There's also channel estimation happening. So there's going to be imperfection from the channel estimation side itself. And there are so many aspects within this communication system which can result in imperfection in this SIC or successive interference cancellation. So as part of this work, what we want to explore is if there is any level of imperfection, are there scenarios where NOMA is inferior to traditional OMA systems? Or does it make sense to always perform NOMA compared to an OMA kind of a scenario? That is what we want to explore as one of the research questions. And what is the impact of this imperfection? Like at what point this imperfection makes NOMA not so feasible or not so relevant in the context of this communication system? And beyond what value of this imperfection, we should probably shift to a OMA kind of a setup or fall back to a OMA kind of a scenario is what we want to look at as one of the potential research questions we try to answer today. So going further, there is also this, just a second. There is also this notion of, reconfigurable intelligent surface, which tackles the second aspect. So NOMA, as I mentioned, is allowing us to pair, let's say, 2 or more users, and they use the same time frequency resource. So it is more from the frequency reuse and the time frequency resource reuse perspective. At the same time, another technology that has been widely discussed and is worked upon in the context of SIC is reconfigurable intelligent surfaces, or RIS. And in the context of RIS, we try to tackle the second problem, which is of coverage. So let's say you have these 2 users, U1, U2, which are, let's say, NOMA users, and they are behind a blockage. Now, can I deploy a RIS considering of, let's say, 10 cross 10 or maybe a larger number of reflective, refractive, or reconfigurable intelligent surfaces? And then can I tune these surfaces, these meta surfaces, so that I'm able to, in some sense, enhance the signal reception at U1 and U2, right? That's the motivation with which we are going to work upon the RIS part. So NOMA provides the resource reuse, and RIS provides extension in terms of coverage. So that is the way how these 2 technologies are complementary also, where we can potentially use them together for better coverage and better signal and better resource reuse within the same network. So with these 2 topics, let's quickly jump into the key issues we are going to look at or evaluate as part of today's discussion. Issue 1 that we're going to tackle is, can imperfect SIC deteriorate NOMA performance beyond OMA performance, like degraded below a OMA system? And 2, what is the impact of imperfect phase compensation in the RIS? So if you recall, here we are tuning these reflectors in some sense, or the meta surfaces in the RIS array, and each of them has to be tuned to a certain angle in the direction of, let's say, U1 and U2. So now there is going to be some optimal angle, but then just like the previous NOMA system, estimation of these angles would typically have certain amount of error, and that is what we are calling as IPC. So in presence of imperfect phase compensation, how much is the degradation in this RIS performance? And then we would like to also see what happens when we are looking at the NOMA system in terms of fairness, and what is the impact of user clustering, let's say 2 users together, or maybe 4 or larger number of users together in a NOMA setup. What is the impact on the performance? What happens? How do we design better power allocation schemes in presence of imperfect SIC and in presence of imperfect phase compensation, right? So those are the key issues we want to tackle today. Please note, as part of the work that I'm going to present, we have derived certain bounds on performance of NOMA with imperfect SIC and imperfect phase compensation. We have utilized these bounds to enhance the NOMA user pairing for a 2-user scenario. And we have tried to create a scheme, a hybrid kind of a scheme, which ensures greater than equal to OMA performance. We want to generalize this to a larger number of users. We also want to look at effects or impact of larger number of users in a NOMA cluster. What happens in terms of fairness? What happens if you're looking at uplink instead of downlink? How can we also plug in machine learning as part of this whole ecosystem? Because that's the flavor of the season these days. So we'll try to look at all those aspects. But first, let's delve into the key problem, which is the imperfect SIC and its impact on NOMA pairing. So just to set up the system, let's say we have a downlink system where we have for any user U on a subchannel, its SINR is gamma U O, where O implements or O implies OMA. So the OMA SINR of any user is the transmitted power from the base station PB, mod of HU square, which is the channel gain in some sense, and divided by the noise and the interference at this particular user IU. Corresponding to this, we can have a rate model using your standard log rate model. The rate for user U can be written as RUO, which is half log 2 1 plus gamma UO, where please note this half additional factor we have considered because we are taking 2 users. So if you have a 2-user OMA system, the 2 users have to be multiplexed either in time or frequency or a combination of 2. They cannot reuse the full time frequency resource at the same time. So that half additional factor is coming to compensate for that. Whereas in the NOMA case, we will not be using this half because they are multiplexed simultaneously in all time frequency resources available as part of this system. So now, given this RU OMA, what we want to do is we want to consider two users, let's say US and UW, as NOMA pairs under the assumption, as I mentioned earlier, where mod of HS square is greater than mod of HW square. And we are going to give a fraction of the base station transmit power PB, let's say delta S to the strong user and 1 minus delta S to the weak user. Now, corresponding to these fraction of power allocated, we can write the respective NOMA SINRs, where gamma SN is the, so the superscript N represents NOMA, superscript O represents OMA. So gamma S NOMA is equal to delta S, which was the fraction of power PB given to the strong user, mod of HS square. And in the denominator, we have the noise plus interference, where interference now has two terms. So N0 is the noise variance in some sense, and IS is the interference from other base stations on the downlink at this user location or user S. We have this additional factor, which has traditionally not been considered in a lot of NOMA works, where this beta represents the imperfection in SIC. So a fraction of the weak user signal. So we are saying the weak user signal has the power 1 minus delta SPB. So a fraction of this is seeping into the strong user's reception, and we are treating that as interference. So beta times 1 minus delta SPB mod of HS square is the interference term due to imperfection in SIC. However, a similar term is not present at the weak user, because at the weak user, we were anyway treating the strong user signal as noise or interference. So for weak user, the NOMA SINR is equal to 1 minus delta S, the fraction of power of PB allocated to the weak user into mod of HW square upon noise plus interference, where interference has two terms. One is IW coming from other base stations in the vicinity of this particular weak user's location, plus delta S PB mod of HW square, which is the strong user signal transmitted by the base station on the downlink, received at the weak user's location. That's why mod of HW square. Now, please note, you can divide both numerator and denominator for both these SINR equations by your N0 plus IS and N0 plus IW respectively, and rearrange terms so that it starts looking in terms of your OMA SINR expression. So I can re-represent gamma SN as delta S OMA SINR of the same strong user upon 1 plus beta 1 minus delta S OMA SINR of the strong user. Similarly, weak users NOMA SINR can be written as 1 minus delta S weak users OMA SINR upon 1 plus delta S times weak users OMA SINR. Given these, we can use the log rate model to say the respective NOMA normalized downlink rates are RSN, which is log to 1 plus gamma SN. Similarly, weak users NOMA SINR is log to the rate is log to 1 plus gamma WN. Please note, for now, we have made this assumption of log rate model, but in real life, we don't use log rate model. In real life, we use this discrete MCS. For example, you have this table in the 4G, 5G standard, 3GPP standard, where there are these 16 or 15 possible levels, where you map based on the SINR thresholds, you map the user to an adaptive modulation encoding index, right? So we also will present some results regarding that in subsequent slides. But for now, given these log rate models, we would like to derive certain bounds, as I mentioned in the beginning of the presentation. So to begin with, we start by treating that the NOMA rate of the weak user should be more than its OMA rate. And then just substituting the rate equation from the previous slide for both these expressions, we derive a upper bound on delta S, where delta S is the fraction of power allocated to the strong user. Similarly, imposing a constraint on the strong user rate that the strong user NOMA rate should be more than the strong user's OMA rate, we can derive a lower bound on delta S. So we have a lower bound, we have an upper bound on delta S. We can also use, let's say, the average sum rate for OMA and NOMA, respectively defined as the sum of RS OMA plus RW OMA as the ASR OMA and ASR NOMA as RS NOMA plus RW NOMA. And we put an additional constraint that the ASR should also be more in the case of NOMA than its OMA counterpart. By using this additional constraint, we are able to derive one more bound on beta, where beta is, please note, the imperfection in SIC. Right? So beta in some sense denote the imperfection. If beta is 0, we have perfect SIC. Right? And as the value of beta increases, there is imperfection. More and more amount of power of the weak user signal seeps into, in terms of the interference term for the strong user's SINR. So given this upper bound on beta, We also apply a positivity constraint on this because it's a non-negative number. So given that, we are able to obtain a lower bound on delta S, and substituting the upper bound of delta S should also be greater than its lower bound, or using this expression, we are able to derive the expression presently on the slide in terms of gamma W OMA should be less than the expression on the RHS. And please note, if you subtract both sides from gamma SO, we get the final expression, which is delta MSD should be equal to gamma S OMA minus the ratio of this expression. The RHS is completely in terms of gamma S OMA and gamma W OMA. So as long as you know OMA SINRs of the strong and the weak user, you can compute the right-hand side of this expression. Now, this is a very interesting expression because it tells us that as long as this delta MSD is greater than 0 or greater than a threshold which the operator can set or the system designer can set, NOMA is going to give you better rate compared to an OMA setup, right? Which is what we are also going to show as part of our numerical results. Now, this is for 2 users, but we will also see if we can generalize this to n user setup in subsequent slides. So now, given this delta MSD and given the bounds on beta and the bounds on lower and upper bound on delta S, we would like to design a user pairing algorithm, which, so this is a joint work between Dr. Moni, who has graduated from our group. She did her PhD with me, and then Professor Prabhat Upadhyay, who is a collaborator of mine from IIT Indore. And as part of the joint work, we have designed adaptive user pairing algorithm while considering this imperfection using the bounds that I have just discussed as part of today's discussion. So given these bounds, there are 3 scenarios possible. First of all, what we do is we take all the users in the system. Let's say there are 8 users. For ease of understanding, I'm taking even number of users, but you can take odd number of users also. If there are 9 users, U5 doesn't get allocated at all, right? So it remains OMA. But if you have 8 users, there is a potential for 4 NOMA pairs, each with 2 users, right? So now, given these 8 users, we'll sort them in the order of their channel gains, right? Or equivalently, you can say we can sort them in the order of their OMA SINRs. So gamma 8 is more than gamma 7, which is more than gamma 6, so on and so forth. So gamma 1 is the least, right? U1 is the worst user in terms of SINR, OMA, and U8 is the best. So we have a sorted array or a sorted list. Given this sorted list, first scenario is we simply pair U1 with U8, the best and the worst users. Similarly, second best U7 with second worst user U2, so on and so forth. Now, we check the middle 2 users in this list. In this illustration, it is U4 and U5. If gamma 5 minus gamma 4 is greater than the delta required, the delta we have derived in this slide, then U5 and U4 can definitely be paired as NOMA users. Their NOMA rates will be more than their corresponding OMA rates. And if that is the case, please note gamma 6 is more than gamma 5 and gamma 3 is less than gamma 4. So difference of gamma 6 and gamma 3 will definitely be more than the difference between gamma 5 and gamma 4. So if for case 1, if gamma 5 minus gamma 4 is more than the corresponding delta, for all the other pairs, NOMA pairs in this setup, their respective gamma strong minus gamma weak user is going to be more than the corresponding delta required to ensure NOMA rate is more than the OMA rate. So case 1 is relatively easy because all users can be paired as NOMA users as long as the first pair, the middle pair in some sense, U5, U4, meet the requirement in this sorted list. However, there is a scenario possible, which is case 2, where gamma 5 minus gamma 4 is less than the delta required to ensure NOMA performance is more than the OMA performance. Now, for such a scenario, one option is we can swap the strong user. So we swap U6 with U5, and we check with U6, is U6 gamma 6 corresponding to U6 minus gamma 4 meeting the requirement of delta gamma 6 comma gamma 4? If yes, we pair U6 with U4 as NOMA user, and we pair U5 with U3 if it is meeting the requirement. If it is not, we keep on swapping U5 recursively, right? However, for case 2, we have assumed at some point U5 is also meeting the requirement. So by swapping certain strong users in this ordered list, we are able to meet the requirement to satisfy NOMA rate is going to be more than the OMA rate. However, there is a possibility of case 3 where the gamma 5 is less than gamma 4, and no matter which strong user we select from group 2, which is the strong user group, the gamma G2 in some sense is the maximum possible. So U8 in some sense, right? So gamma 8. So if gamma 8 minus gamma 4 is also less than the delta, then we effectively say U4 cannot be paired and we will not pair U5. So we let the U4, U5 be as OMA users, and we check for the next pair, which is gamma 6 and gamma 3. Assuming gamma 6 and gamma 3 meet the requirement, we let them be NOMA users. If they also don't meet the requirement, it can be a recursive case 2, where we swap U6 with U7, U8, so on, and check. Maybe it meets the requirement after swapping, we let them be NOMA. If U3, U6, after swapping of U6 also doesn't meet the requirement, we simply let U3, U6 also as OMA users, so on and so forth. So worst case scenario in case 3, all pairs are not feasible. We allow all users as OMA users. Best case scenario is case 1, where all users are paired as the NOMA user, right? Now, given this is the same thing illustrated as an algorithm where we have this group G1 and G2, and then we are trying to figure out this allocation or this pairing of users for 2-user pairing in the NOMA scenario. Right. Now, given this algorithm, we'll go into some numerical results and then we'll try to analyze certain aspects from that. One is, if you see here, the x-axis is beta, which is the imperfection in SIC. That's the term in the denominator of the strong user. Now, given this imperfection, as the imperfection increases, please note the OMA rates are not going to change because the OMA SINRs are not a function of beta. So ASR OMA, which is the orange circle, and similarly the strong user OMA rate, which is the pink, if I can call it, squares, and similarly the process for weak user OMA rate, they're constant. They're not changing with beta. Same is true for weak user NOMA rate, because for weak user, if you recall, we are not performing any SIC. We are simply considering the strong user signal as an additional noise and interference term. So weak user NOMA rate, the triangle, brown triangle, is also constant with respect to beta, right? The only thing that changes effectively is the strong user's NOMA rate, as denoted by the blue star line. And as imperfection increases, this rate drops. Again, this is for the log rate model, because the denominator term has a beta, so that as beta increases, there is a decreasing trend we observe in terms of the rate of the strong user. At the same time, for ASR, the average sum rate also, because ASR is sum of these two rates, there is a similar trend observed. So two things here, two interesting observations. One is there exists a value of beta beyond which the strong user's NOMA rate is lower than its corresponding OMA rate. So this goes against the conventional hypothesis that NOMA is always better. It essentially shows that NOMA is not always better in presence of imperfection in SIC. So for a practical setup, you have to be careful where to use NOMA and where to use OMA. If the imperfection at the strong user, if the beta at the strong user, and again, in the illustration of the results that I've shown, I've taken the same beta, but you can solve this with different beta, user-specific beta also we can look at. But for now, assume the hardware has on an average same beta, the strong user rate drops below its OMA rate, and correspondingly, the ASR also drops below its, the ASR NOMA also drops below its OMA ASR, right? So there is this value of beta, after which it makes sense to go for OMA and not NOMA, right? That is one. Two, if you're going to simply maximize ASR, if you're going to do allocation to maximize ASR, it's going to be a biased allocation, because as you see here, the allocation is more in favor of the strong user, right? The weak user rate is marginally better than its OMA in terms of the NOMA rate of the weak user. So again, there is this issue of fairness. How can we be more fair in allocation of the power between the strong and the weak user within NOMA in presence of imperfection in SIC, so that the strong user also gains by performing NOMA, and most of the gain is not transferred only to the, so the weak user also gains. The strong user is not the only one gaining out of the NOMA pairing, right? So those are the issues we would like to tackle as we go forward in today's discussion. So Again, as I mentioned, we not only generated the results for the log rate model, but we also generated the results for a discrete rate model. So here we have used, as per the 3GPP standard, the mapping from the SINR to the adaptive MCS, modulation and coding index based allocation for each user. And using adaptive MCS, as you see here, there is a discreteness in the rate. So based on the MCS used, you have the spectral efficiency, and given that, you can compute what is the corresponding ASR OMA or ASR NOMA, and similarly for the strong and the weak user, the OMA and the NOMA rate. Please note, as mentioned in the previous slide, the OMA rates are not going to change with imperfection, increasing imperfection in SIC. The weak user rate is not going to change for OMA as well as for NOMA. It is only the strong user rate, the one in blue star, and the ASR, which is the sum of these two, which varies as we increase the beta. However, a similar trend is observed even for discrete rate model. So even for a practical discrete rate model that is currently being used as per the 3GPP standard, there is a value of beta after which NOMA performs inferior in terms of the rate of the strong user compared to its OMA rate, and same is true for the ASR. So it's not just the log rate model, it's not just the theory part, but even in a practical setup, you are going to see loss in performance if the imperfection is beyond a certain value. Now, given this, we also looked at variation of the fraction of power between the strong and the weak user. And as the fraction of power increases, delta S increases, the strong user rate keeps increasing, the weak user rate starts dropping. Because please note, the numerator of the weak user rate also had this fraction of 1 minus delta S. So as delta S increases, the weak user rate drops for the NOMA case, which is what is visible here. And the strong user and the average sum rate both increase for NOMA if the allocated power is more for the strong user. However, there is again a point. So if you allocate too much power to the strong user, there is a scenario even in the NOMA context for low value of beta, let's say beta equal to 0.02, there exists a value in alpha S domain that beyond that fraction, if you allocate more power to the strong user, the weak user's rate is going to drop below its NOMA rate is going to drop below its corresponding OMA rate. As you see here, the brown triangle, as the allocation for the strong user increases, the weak user rate in NOMA drops below its corresponding OMA rate. So now we have these two parameters that we have to be careful of in terms of the allocation, not just the imperfection, but also the fraction of power allocated to the strong and the weak user. So we have to be careful regarding both pairing as well as the power allocation in the context of NOMA to ensure fairness between the users and to ensure the NOMA rate for the system as well as the individual users is higher than their corresponding OMA rates. We did the same experiment with the discrete rate model, and we saw or we observed similar trends. So as you see here, as the power allocation for the strong user increases, the weak user rate drops in the discrete rate model also drops below for the NOMA scenario compared to its corresponding OMA rate. Right. So now, basis this, we try to optimize the setup for various values of imperfections. Let's say 0.2, 0.5. We try to characterize the performance in terms of various number of users. And we compared with the state-of-the-art algorithms available for user pairing at that point of time, which were NF, RP, and UCGD. And we were able to show gain in ASR compared to the state-of-the-art schemes at that point of time, which were not considering imperfections in SIC. So in our simulations, we have added the imperfection in SIC and then tried to regenerate the result for those schemes to be fair in our comparison. So this was as far as a two-user pairing scenario goes. Now for the next couple of slides, I'll try to see if we can generalize this to various aspects of NOMA. The first aspect that we tackled is what happens if you want to generalize this to n-user NOMA instead of just two-user NOMA setup. So as part of this patent, and the good thing is I have not updated the slide, but this patent has been granted, I think, 2 days ago, where as part of this patent, we have been able to show that you can have larger number of users in a NOMA cluster. It doesn't have to be only two-user NOMA pairs. You can have a larger number n. For this illustration, for example, let's say there are 16 users. So we are sorting them. So you can assume the same sort of sorting where gamma 16 is the highest, gamma 1 is the lowest. So we arrange them, we order them in the following fashion: U1, U2, U3, U4, U5, U6, G7, U8, so on and so forth. And then we cluster them into 4 user clusters. So the bottom cluster, U1, U5, U12, U16, as you see that the index itself has certain gap, is 4 or larger number apart, right? So the assumption is gamma 16 minus gamma W would be larger than required threshold. I am not presenting the theoretical result here, a part of which has been published in this paper in CompStats earlier with a couple of other collaborators. The journal version is under review. However, what we have been able to show is even for n user clustering in the context of NOMA with imperfection in SIC, we have been able to derive certain bounds on both the power allocation factor delta as well as the imperfection in SIC and a recursive bound on delta between users in the same clusters. So we have been able to derive a recursive bound on delta of gamma 16 and gamma 12, delta of gamma 12 and gamma 5, and delta of gamma 5 and gamma 1, which as long as those 3 delta bounds are satisfied, you can cluster these 4 users together in a NOMA user cluster, and their individual NOMA rates will be more than their corresponding OMA rates if we had not clustered them together, right? So given those bounds, given that MSD criteria, if it is satisfied, we cluster these 4 users together as a NOMA cluster. However, there is a scenario possible, let's say for the top cluster, U8, U4, U8, U9, U13, because U4 has gamma 4, which is higher compared to U3, U2, and U1. Similarly, U13 has gamma 13, which is lower. The SINR OMA is lower compared to U14, U15, U16. There is a scenario possible, and especially for U8 and U9, for example, there is a scenario possible that gamma 9 minus gamma 8 is not meeting our recursive NOMA requirement. So if that MSD criterion is not satisfied, we don't cluster these 4 users into a NOMA cluster. We split it into 2 users, U4, U13, which are far apart. So hopefully they will meet the NOMA requirement for 2 users that we've already discussed in the previous slide. And U8, U9, maybe because they are the closest users in terms of their channel gains or difference of their SINR in some sense for this particular algorithm. If gamma 9 minus gamma 8 doesn't meet our 2 user NOMA pairing requirement, we simply let them be as OMA users. Now, this is for the first group, and we can recursively keep doing this for any number of clusters which are not meeting the overall 4 user NOMA cluster criteria. So then we break them into 2 user NOMA clusters, and then we apply the 2 user NOMA criteria presented in the previous slide. What we have been able to do is we have been able to derive this recursively for any 2 to the power n kind of a user cluster. So for any 2 to the power n user cluster, we have an expression. If all users recursively meet that expression pairwise, they can be paired as NOMA users in presence of imperfection in SIC. If not, we can split them into smaller clusters, and for each cluster, recheck recursively whether the subcluster meets the NOMA requirement or not, and then correspondingly decide how many users to be clustered together as a NOMA cluster and how many users should be let as OMA users only. Right. So this was one aspect where we wanted to generalize from 2 user to n user scenario. And we have derived and we have obtained some numerical results where, in some sense, if you look at the spectral efficiency, please note the higher number of users together in a NOMA cluster is expected to give more performance in terms of, let's say, mean spectral efficiency. As seen here, for 8 users, the performance is more than for 4 users, which is more than for 2 users. However, with imperfections, increasing imperfection beta, the impact becomes more prominent with a lower user, setting for traditional algorithms. For example, NF, which is a 2-user pairing algorithm, it starts performing below the OMA baseline for very smaller value of beta, whereas our proposed work, even for larger number of users in a NOMA cluster, significantly outperforms OMA for a larger beta, right? That is one. Then the second aspect that I mentioned in the beginning for a 2-user setup, and we also saw this as part of the numerical results, that it's predominantly the strong user rate which is dominating because we are trying to maximize the ASR in some sense, which is not a good objective in the first place, right? We want to have a balance between performance of the strong user and the weak user in a 2-user NOMA pair. So as part of this work, what we have done is we changed the objective to a utility function, which is an alpha fair scheduler or an alpha fair utility function, where u alpha is x to the power 1 minus alpha upon 1 minus alpha for alpha greater than 0, alpha not equal to 1, and it is log x for alpha equal to 1. So in some sense, you can take this u alpha for different users and combine it for alpha equal to 0. This is nothing but sum rate maximization. So for alpha equal to 0, if you're taking if you look at T alpha, for example, for alpha equal to 0, it is nothing but RSN plus RWN. Strong user NOMA rate plus weak user NOMA rate, average of that, half of that, right? Which we have seen previously that it is not a fair, it results in unfair allocation between the strong and the weak user. Now we can take alpha equal to 1, which is something like RSN into RWN to the square root of the two values. Or you can take a larger value of alpha. You can take alpha tending to infinity or very large value, let's say alpha equal to 40 or something. And that tends to a max-min kind of a approach where we're trying to maximize the minimum possible rate in the system, right? So as part of this work, we were able to show that if you take this alpha pair scheduler, instead of simply maximizing the average sum rate, we are able to get certain level of fairness between the different users which are part of this particular network. Another aspect that I highlighted in the beginning is, can we do some sort of machine learning or apply some machine learning as part of this or to tackle this particular problem statement? So we, again, for this particular work, what we did was we divided it into two problems. Please note, the first problem is whether we should perform NOMA or not. So it's like a standard classification problem. So we have PC equal to 1 if it should be a NOMA cluster for these two users, and PC equal to 0 if they should be OMA users. So we trained a standard random forest kind of a classifier. The input was the OMA SINR of the strong user and the weak user, the imperfection in the system beta, and some fairness notion in terms of alpha. So the same fairness notion that I discussed here, right? So given this notion of fairness, and this can change from operator to operator. So it's like a design parameter that an operator can optimize on. So given alpha, beta, gamma is gamma W, we first did a classification using random forest-based classifier to decide whether these two users should be NOMA users or they should be OMA users. Given that they should be NOMA users, then we applied a deep neural network technique for, in some sense, for a regression kind of a problem where we are trying to predict delta S. What is the fraction of power to be allocated to the strong user? And correspondingly, when minus delta S to be allocated to the weak user, where again the input is gamma S, gamma W, beta, and alpha. And we were able to show certain gain in performance using this two-step approach of classification and regression for NOMA clustering and power allocation for a NOMA pair. We further extended this work to both downlink and uplink, where we looked at what happens if you have different type of strategies. So as you recall, based on alpha, we can have, let's say, a max-min kind of a scheduler, or you can look at a fair scheduler with some notion of, let's say, alpha equal to 1, or you can have a greedy scheduler, which is just trying to maximize the system sum rate in some sense for alpha equal to 0, so on and so forth, right? So there are different strategies possible. And for each of those strategies, we were able to derive for a two-user setup in uplink, as well as in a two-user setup in downlink, what should be the pairing criteria. At the same time, we were able to derive the fraction of power that should be allocated to the strong and the weak user in downlink and to the strong and the weak user in the uplink, right? I'm not going to the detailed derivation of this because in interest of time, otherwise, I would have exceeded the limit of 50 minutes that has been given to me by the organizers, ballpark. However, those interested can check out, this is available on IEEE Explore. It also got the poster also got the Best Poster Award in CompScience 2023. We also applied this for a practical scenario of UAV communication. In the context of UAV communication, we have this thing called a short packet communication. So we were able to rederive all the results for a two-user NOMA pairing in the context of a drone or a UAV-based NOMA setup, where short packet communication is being used. This is a joint work with Dr. Yeduri. He's a postdoctoral fellow with Dr. Linga Reddy, who is a collaborator of mine from University of Agder, Norway. And for another extension of this work that is possible is on top of this, so far we have only derived bounds on power allocation. We have derived bounds on imperfection. Using that, we have created or we have proposed an algorithm for user pairing as well as for power allocation. Now, given all of this, can we do some sort of scheduling, right? So we tried to approach that problem as part of this particular work, where we looked at scheduling in time domain. So it's a simple time-based scheduler. And for every fraction of time, we are deciding whether NOMA for 2 users or they should be OMA in different time slots. If they are NOMA users in the same time slot, then what should be the power allocation between these 2 users, right? So we again derived some results in terms of the time fraction as well as in terms of and reused our results for power allocation as well as the user pairing algorithm that I have presented in the very beginning of this particular talk. Now coming to the second part. So far all the works that we have discussed is pertaining to NOMA in presence of imperfection in SIC. Now we would like to extend this to NOMA with RIS. At that point of time when we started working, the RIS was more commonly called as IRS, the intelligent reflecting surfaces. But then over a period of time, people realized it need not always be reflecting. It can also be refracting, diffracting, doing all the other changes into the wave possible as a surface. And that's why it is now more common to use RIS, reconfigurable intelligent surface, instead of IRS, which is intelligent reflecting surface. But then to maintain correctness with the original work, so Dr. Pavan did his PhD in our group. I'm his co-guide in some sense. He's currently, I think, a faculty in IIT Mandi. So as part of this work, what we did was we looked at if you have an IRS-based setup to enhance coverage, where let's say there are these 2 users, user 1, user 2, behind a blockage, how do we tune the angle of each of these reflectors in the IRS to maximize certain aspect, let's say data rate or SINR for user 1 and user 2, assuming user 1 and user 2 are NOMA paired. So same problem, we have also looked at, so this is from the downlink perspective, and then we looked at the same problem from the uplink perspective, because in uplink, the problem is slightly different. In uplink, you have fixed power available at each user. So there is no power allocation happening in terms of splitting the power. In downlink, we are splitting the power, right? So if you have the base station, it has PBS. We are dividing delta S PBS for user 1, 1 minus delta S PBS for user 2, if they're in a NOMA pair. But in uplink, this is not true. User 1, the mobile equipment, has its own power, PU. Similarly, user 2 also, the mobile phone has its own power, right? We do some sort of power control on top, which is required to mitigate interference with the nearby cells. But apart from that, there is no requirement to split the power between the user 1 and user 2, right? They are different devices for that matter. So that's why we revisited the same problem from an uplink perspective with imperfection in phase compensation for an RIS-assisted uplink NOMA system. From a use case perspective, we looked at RIS-assisted NOMA V2X system with IPC, where we applied for a V2X communication setup. This is a more recent work with Swaraj and others, where we try to apply this in the context of vehicle to vehicle, vehicle to infrastructure kind of a communication scenario. So that was by and large what I wanted to highlight. We have also been working in other aspects of NOMA and SIC, for example, for visible light-based communication system. Dr. Uday, he did his PhD in a group. Dr. Natarajan is a collaborator of mine from my institute, my department. So we looked at NOMA in the context of VLC. We have also looked at NOMA in the context of relays, or NOMA or successive interference cancellation in the context of IoT or machine-type communication devices. But then if any of you is interested in those type of topics, those type of areas, please feel free to reach out to me and we can explore some sort of collaboration there. But I just wanted to highlight this also to give you a flavor of various works happening in our group. To add more, so that's by and large what I wanted to share today as far as the technical part of the talk goes. The remaining part of the talk is more in terms of other research areas, work happening in our group, and some of the other collaborations I wanted to highlight. So maybe just 1 or 2 minutes on this, and if there are any questions, I'd be very happy to answer them. So today I presented NOMA and RIS with imperfect phase compensation and SIC. but we are also actively working on OTFS and ISAC. I am an affiliated faculty member with the Department of Artificial Intelligence at IIT Hyderabad. Initially, I started working at the intersection of ML, DL, and COM, but of late, some of the PhD students in our group have been working purely from a AI perspective. So there is also work happening in domain adaptation and domain generalization. I just wanted to highlight this because please note, for example, for the ML work that I presented today, or at least the slide I presented today, there we have assumed labeled data is available for the environment. So even if you're training a DNN, you have this labeled data set available, you train the DNN, and then the test data is coming from the same environment in some sense, even if it is a simulated environment. However, in real life, this may not always be true because you change the location all the time. Let's say the talk is being organized in ISC. You have such a big, huge, beautiful campus. Now you may do the training for a particular building. And now when you change the location, the channel or the environment is going to change significantly. So now do we retrain the model every time? Or do we collect so much data across the whole campus so that we can have these trained models based on the location? But that is very time consuming. It's also very cost intensive and computationally intensive in terms of both training as well as testing. So one potential approach is, can we use domain adaptation, where in domain adaptation we say, okay, during the training time we have sufficient data from one set of one class of data. We also have, let's say, some unlabeled data from the test perspective. So maybe between the training data and the test data, there is a change in terms of the distribution. It could be change in terms of the mean, in terms of the variance, or any other statistical property of the test and the training data. So now, and this will happen invariably if the environment is changing, right? So now if the environment is changing, instead of retraining the model on this new environment, or where the distribution of the data for the test case has changed, can I reuse the trained model from the training data by simply putting in some of the test data without any labels during the training time? So that is what domain adaptation is all about. Similarly, in domain generalization, we don't even assume unlabeled test data is available. We say, okay, the model has not seen the test data at all, which is more practical from a wireless communication perspective, where you have, let's say, training done in a particular environment in a lab, and now you want to deploy this model for a test setup in third-party locations. With minimal changes in this model, how can I reuse this? But of course, the work we have done so far for both the domain adaptation and domain generalization is more from the computer vision side on publicly available data sets. However, at this point of time, we are actively working on applying these vis-a-vis the communication system that we have discussed in today's talk. I would also like to acknowledge a couple of industry partners. So we have generously been funded by Suzuki Motor Corporation Japan, NTT Japan, and ZF India. So I just wanted to acknowledge their support. I would also like to acknowledge support from Ministry of Electronics and Information and Communication Technology for my fellowship, as well as for funding projects, and also DST for generously supporting several projects in our group. And I would like to acknowledge IIT Hyderabad for all the support they have been giving to me as part of the ecosystem, due to which I've been able to pursue all these interesting areas of research. With that, I will skip the slide on IITH. I don't think I need to give that detail to you guys. However, I am currently a TPC chair for CompScience 2026. The regular paper deadline is done. However, the workshop and the poster and the call for demo is still open. My sincere request is, if any of you is interested, has an ongoing work which you'd like to submit, please do explore. This is happening in Bangalore, so definitely for ISC folks, it's not very cost intensive to attend this conference. So I humbly request you to consider submitting at least a poster or a workshop paper here. I would also like to invite all of you to National Conference on Communications, our IIT Hyderabad, in collaboration with IIIT and a couple of other institutes. We are organizing this in 2026 towards the end of February. The call for paper is now available. You can go to EDAS or go to the webpage for NCE 2026. Please, the regular paper deadline is still there. We are going to extend it further by a couple of weeks. So please consider submitting a paper to this. We are going to conduct it completely in our campus. There is a full-fledged guest house for around 200 people, and a student hostel accommodation is also there. So you are most welcome to please submit a paper and also participate in both the conferences. That was by and large what I wanted to share. Thank you again for inviting me for this particular talk. I would be happy to answer any comments or queries if they're in the chat window, or please feel free to unmute and ask. Thank you.
Thank you very much, Professor, for accepting our request and delivering a very interesting talk. We request the audience to ask questions if there are any. I think your talk is very clear for everyone, Professor. Thank you once again for for giving such a wonderful talk. And audience, thank you all for attending and have a great evening. Thank you.
Thank you. Thank you again for inviting me. Have a good day. Bye.
Bye, sir.